Outcome 1, Lesson 2, Coulomb's Law. We'll start with Part 1, an introduction to Coulomb's Law. Recall from the last lesson how we can use the law of charges to tell us the direction of our electrostatic forces. The law of charges tells us that unlike charges attract, which means that they experience forces in the direction towards each other, and like charges repel, which means they experience force in the opposite direction. Coulomb's law is a formula that allows us to calculate the magnitude of the force between the two charges. Coulomb's law is written like this: F equals K Q1 Q2 divided by R squared. In Coulomb's law, F represents the force between the two charges. This is measured in newtons. Q1 and Q2 are the charges that are experiencing the force. They're measured in coulombs. R is the distance between the centers of the charges. R is measured in meters. And K is a value called Coulomb's constant. The value for Coulomb's constant is 8.99 times 10 to the 9 Newton meters squared per Coulomb squared. Don't worry too much about those units. They're mainly there just to make sure that the units work out in the formula. Coulomb's law gives you the magnitude of the force only. It is up to you to use the law of charges to determine the direction, remembering that unlike charges experience forces towards each other, and like charges experience forces away from each other. Here's an example of using Coulomb's law. What is the force on the 3 microcoulomb charge? Coulomb's law says that F equals K Q1 Q2 over the separation distance. This is 8.99 times 10 to the 9, which is Coulomb's constant, times the magnitude of the two charges. We have -2 microcoulombs, which means times 10 to the minus 6, times 3, again in microcoulombs, which is times 10 to the minus 6, divided by the separation distance of 0.15 squared. Be really careful when you're doing Coulomb's law calculations. It's really easy to forget to do the squared. Don't drop the squared, especially in your calculator. Sometimes students will actually write it out in the question and then just forget to hit the squared button in their calculator. This gives us a force equal to 2.4 newtons. Remembering that Coulomb's law will only give you the magnitude of the force, and since force is a vector, we need to have the actual direction as well. Since these are unlike charges, we've got a negative and a positive, we know that they attract. The 2 microcoulomb charge is attracted to the 3, and the 3 microcoulomb charge is attracted to the 2. Since we're interested in the force on the 3 microcoulomb charge, we look at that direction, which is to the left. So the force on the 3 microcoulomb charge is 2.4 newtons to the left. Part 2 looks at Coulomb's law and graphing. This section is important because it shows you how Coulomb's constant is calculated using experimental data. But first, there are 3 common graph shapes that you will encounter in Physics 30. The first is linear. A linear graph will always form a straight sloped line and will have an equation that looks like y proportional to x with no exponents. You should also be able to recognize a parabolic graph. A parabolic graph is curved, like a parabola, and will always have a formula that looks like y is proportional to x squared. The last type of graph you should be able to recognize is an inverse square graph. This one is curved, but it's decreasing down, and this has an equation that looks like y is proportional to 1 over x squared. The inverse tells you about the fraction, the 1 over. The squared tells you that the x value is squared. Coulomb's law belongs to a family of formulas called the inverse square laws. The inverse square laws all have inverse square shaped graphs and formulas that look like y equals 1 over x squared. Universal gravitation formula that you learned in Physics 20 is one of these laws. This one looks like F equals g m1 m2 over r squared, where the r is the inverse square. Coulomb's law looks very similar to universal gravitation. F equals k q1 q2 over r squared, where again the r is the 1 over x squared part of the inverse square relationship. In this lesson, we will use curve straightening techniques to determine Coulomb's constant using graphical data. For this example, we will look at the electrostatic force of a rod on a pith ball. The pith ball has a charge of 10 microcoulombs, and the rod also has a charge of 10 microcoulombs. As it's brought near, the pith ball moves, and as a result, there is a force on the pith ball. We're going to be graphing the data from the movement. As the rod is brought closer and further from the pith ball, the force in newtons is given with respect to the distance of the rod. So we start by plotting the data on a graph. Force is on the y-axis, and the distance between them is on the x-axis. When you connect the data points, we see a curve that drops down increasingly towards the x-axis. This graph demonstrates the inverse square shape. There's not much we can gain from this graph other than recognizing the shape of the formula, but we can use a method called curve straightening to find out exactly how much it's dropping by and give us the value for Coulomb's constant. Curve straightening means that we take the inverse square graph and we turn it into a linear graph. To do this, we take the axis that the graph is curving towards and we inverse square it. So instead of plotting r on the x-axis, I'm going to plot 1 over r squared. 1 over 0.1 squared is 100. 1 over 0.2 squared is 25. And the other data points are calculated similarly. We then take our force data and our 1 over r squared data and plot it on the graph. Again, force is on the y-axis, but this time 1 over r squared is on the x-axis. Plotting our data points should give us a linear graph. Connecting the points as a best fit line gives us our linear graph, and we can calculate the slope of this linear graph using the slope formula. Slope equals y2 minus y1 over x2 minus x1. Since the points 90 and 100 and 2.5 and 2.8 fall on our graph, I'm going to use those points for my slope calculation. 90 minus 2.5 divided by 100 minus 2.8 gives us a slope equal to 0.9033. We need to figure out the units of our slope. Since slope is calculated by y divided by x, the slope units are newtons divided by 1 over meters squared, which gives us a slope unit of newton meters squared. Taking this slope, we can then examine the formula to see how we can use this to find Coulomb's constant. Since the formula for Coulomb's law is F equals K Q1 Q2 divided by r squared, which is the same as multiplying by 1 over r squared, we can compare this to the slope-intercept formula, y equals mx, where we note that we plotted f on the y-axis, so they line up, and we plotted 1 over r squared on the x-axis, so they line up. Therefore, the slope should equal k q1 q2, and k equals the slope divided by q1 q2. This gives us k equals the slope over q1 times q2. And from the original example, we see that both the pith ball and the rod had a charge of 10 microcoulombs, so k is equal to 9.9033 newton meters squared divided by q1, which is 10 microcoulombs, and q2, which is 10 microcoulombs. This gives us a k value equal to 9 times 10 to the 9 Newton meters squared per Coulomb squared. Part 3. Coulomb's law and vector addition. If there are more than 2 charges in a problem, the electrostatic forces combine to produce a net force. Remembering that force is a vector, therefore vector addition techniques must be used to combine the forces. In this example, we want to calculate the force on charge 3 due to charge 1 and charge 2. Charge 3 is negative, which means it's repelled from charge 2. So the force from charge 2 on charge 3 is going to be towards the right. Charge 3 is attracted to charge 1 because charge 3 is negative and charge 1 is positive, which means there's also going to be a force on charge 3 towards charge 1. We'll start by calculating the force of charge 2 on charge 3. This is given by k q2 q3 divided by the distance between them squared, which is 8.99 times 10 to the 9, which is Coulomb's constant, times charge 2, the magnitude only because we work out the direction ourselves later, which is 2.3 times 10 to the minus 7, times charge 3, which is 3.5 times 10 to the minus 7. Again, even though charge 2 and 3 are negative, we don't put the negative signs in because we determine the direction ourselves. Coulomb's law will not give us direction, so we don't want to get confused by extra negatives sticking around. The distance between them is 1.7 meters, and this is squared. This gives us a force equal to 0.25041 newtons to the right. The second force is the force of 1 on 3. This is k q1 q3 over r squared. 8.99 times 10 to the 9 is Coulomb's constant, times q1, which is 1.5 times 10 to the minus 7, and q3, which we're going to enter only as positive because the negative sign refers to charge and not direction, divided by the distance between them, which is the total distance, which is 1.7 plus 1.4 squared. This gives us a charge of 1 on 3 equal to 0.049119290 newtons, and this is to the left. Using these two forces, we can find the total or net force on charge 3. Let's call this F3 net. F3 net is going to be F1 on 3 plus F2 on 3. Negative 0.049119290, negative because it's to the left, plus 0.250413, positive because it's to the right, which is a total F net on charge 3 equal to 0.20 newtons. And since it's positive, it's to the right. These calculations get a little bit harder when we've got forces at angles. For example, here we're going to have perpendicular vector addition. We're looking for the force on charge 2. Now, there's going to be two forces on charge 2, the force of 3 on 2 and the force of 1 on 2. Since they're all positive charges, these are all going to be repulsive. So, charge 3 repels charge 2, so it has a direction to the left. Charge 1 also repels charge 2, so it has a direction of force that's downwards. We'll start by calculating the force of 3 on 2. This is given by K, Coulomb's constant, times the charge of 3 times the charge of 2 divided by the distance between them squared, which gives us a force equal to 22475,000 newtons to the left. Charge 1 pushes on charge 2. Similarly, K, Q1, Q2 divided by the distance between them squared gives us a force 1 on 2 equal to 199,777,777 newtons, and this one is down. To determine the net force on charge 2, we use vector addition techniques. F2 net has a magnitude equal to our two forces squared and square rooted, which gives us a force equal to 3.0 times 10 to the 9 newtons. The angle is given by tan negative 1, 22475,000. This is to the left, divided by 199,777,777, and this is down. This gives us an angle equal to 48 degrees left of down.